Hi, my name's Andrew McLaren, and I'm going to help you understand lattice energy so that you can solve problems like what we have here, as well as problems like this. So there's a lot of parts going on here, but to be able to make these diagrams yourself, we really need to go big picture on this. And if you know a little bit about charges, it's going to really help out. So if I have a positive and a negative charge, and those things move towards each other, you should be familiar with an energy change. It's kind of like a ball rolling down a hill. So if we're talking about the change in H for two opposite charges falling towards each other, it's kind of like a magnet getting attracted to itself, or in electricity, electrons getting attracted to a more positive side of the circuit. So this should be something that happens on its own. This is going to be releasing energy. And so when we're talking about gases, these things that are like really far away from each other, like all these gas molecules kind of coming together and having this attractive force um, of these opposite charges getting brought together, that should end up forming a lattice with a bunch of positives and negatives next to each other. They're closely and strongly interacting with each other. And the exact pattern is going to vary depending on whatever type of crystal we're talking about. But generally, that energy change can be thought of as something that releases energy. And that amount of energy that comes from when we have these positive and negative ions as gases falling towards each other is described as lattice energy. So if you separate those solids and then turn them into gases, that is kind of going the opposite way. So if we are then deciding to separate the positive and negative charges, then you're going the other way in this situation, and the change in H should be positive. So if you're trying to relate all these different steps in this process, that idea of sign here is going to be very, very important. So there's also this problem I've already got it kind of worked out. We do have to consider the amount of energy released for a reaction per mole of that reaction. So this one that I've got marked as kind of blue, it's got 8 moles of magnesium reacting with 1 mole of this sulfur in a compound where there's 8 of them to get this magnesium sulfide. But there's 8 moles of there being made in that reaction. So this is the energy that's released if you use 8 moles of magnesium to make 8 moles of magnesium sulfide. If we're trying to relate the amount of energy going from 1 mole of magnesium and 1 mole of sulfide to making 1 mole of magnesium sulfide, we have to do some multiplication or division that's appropriate. So you'll see that the value that I have is not this negative 2,741, but it's actually that number divided by 8. I've also reversed the reaction. So instead of having that energy being released in that process, I'm considering that energy being added to the system. So there's a number of other similar things that we're going to have to do oftentimes in these problems where it's like, oh, that's 8 sulfurs. I'm really asking what's going on when I just have like 1 sulfur or 1 mole of sulfur. So I need to divide that number by 8 as well. If you get confused with the signs on some of these things, generally speaking, I like to think about ionization energy as like you're taking an electron away from a positive charge. So generally speaking, ionization energy is a positive value, and electron affinity is going to be something that's a negative value. So when you have an electron fall towards a nucleus, then that is going to be something that generally is releasing energy as well. So oftentimes you'll see electron affinities kind of going down in these diagrams, but that's because you're having electron fall towards a positive charge. You may have noticed in this other example problem that I was just showing that the electron affinity, the value that's for this kind of electrons getting attached here is a positive value. That's because you have a sulfur that's becoming 2-. So if you have 1 electron affinity for just a single sulfur, that actually would be a negative number. But because you have a negative charge that you're having another negative charge get attracted to, that is something like rolling a ball up a hill. So that change in energy for that second electron getting attached is very, very, very positive. So sometimes in these problems, electron affinities will be positive. Just keep that in mind, especially if you're putting multiple electrons on. That might end up being a different sign than what you expect. But generally speaking, you do see electron affinities, especially if it's just for a single one, kind of going downward. Now I used the scaffolding of sodium and chloride reacting to do this problem, but this was actually for a different compound. This was for potassium bromide. In that context there, you can see that the electron affinity for the bromine was negative, so this was pretty good like structure to use for doing the problem. And generally speaking, I think of the ionization energy as a negative change because it's the amount of energy released when we form this lattice, like these gases falling towards each other. So you can think of that as a negative number, but in doing so, usually you're given a change in H value. Like in this problem, they talked about the H of formation of KBr. So that's going from something that's kind of like this, but instead of sodium and chloride, this would be like potassium and bromide. And instead of forming the solid compound here, we're kind of going the other way. So we need to account for that energy change to be positive. And that's a pretty common thing that you'll see in these types of problems. So knowing the positive negative relationship in terms of like separating charges or having them falling towards each other is very, very useful in these types of problems. So you can also see it in this problem here. We were talking about that H of formation, which was a negative value here, but we were trying to kind of get the last energy, so we were considering going the other way with all of these other steps, so that we could figure out what this would be going downward. So that's the big picture on Born-Haber cycles. Trying to relate all these things to each other, you have to keep it per mole appropriately. And generally speaking, the electron affinity will bring us down a little bit, and ionization will go up a little bit, but it's not always that simple, as we saw in this problem here. Let me know if you got any more questions. Thank you for joining me.